In Lecture 20, we're going to begin looking at the sum and difference formulas for some of our trig functions. We're going to use these sum and difference formulas to find exact values. We're going to use the sum and difference formulas also to establish identities, and then also look at how they might be used when trigonometric or inverse trigonometric functions are involved. But first of all, we want to show where they come from. We don't accept formulas at face value. We've got to prove them. We've got to show that they are in fact true. Let's start by looking at the sum and difference formulas for cosine. And I am going to go ahead and just write them down to begin with, but then we're going to show where they come from. So to begin with, the cosine of alpha plus beta is always equal to, for any alpha and beta, cosine of alpha cosine of beta minus sine alpha sine beta. Similarly, cosine of alpha minus beta is cosine of alpha cosine of beta plus sine alpha sine beta. Now, to see where this comes from takes just a little bit of some algebra, but also just looking at a couple of pictures. Let me consider two drawings for you. Let's start by drawing two angles, alpha and beta. Let's say alpha happens to be this angle right here. All right, so that right there is, we'll call that alpha. And let's have another angle, maybe this angle right here. Let's call that beta. Okay. Now, if I were to draw the unit circle on this graph, we know that where the angle beta intersects the edge of the unit circle has coordinates cosine of beta, comma, sine of beta. Because that's the definition of cosine and sine, the x-coordinate and y-coordinate of where the angle beta intersects the unit circle. Similarly, this angle over here is going to be, or this point over here is going to have coordinates cosine alpha, comma, sine alpha. Let me rewrite alpha. All right, then I want you to think about what is this angle right here equal to, that angle inside there. Since it's all of alpha with beta removed, this angle turns out to be alpha minus beta. Okay, something like that. So what I'd like to do is now let's redraw that same picture again, only now the angle I want to draw is this alpha minus beta, which appears to be about this big, say. So that's right there, alpha minus beta. So if we were to draw our unit circle on the outside of this, the coordinates of this point right here would be cosine of alpha minus beta, comma, sine of alpha minus beta. And the point here, of course, is, don't do that, 1, comma, 0. Now, the reason I want us to consider these two pictures is this line, in fact, I'll draw it in green here to give it a distinct color. The line from here to here, this straight line, has the exact same length as this line right here. Right? Because it's the same angle swept out inside here as what is swept out inside here. And these both are unit circles, so these two lengths are the same. And surprisingly, knowing that fact is enough for us to derive our cosine alpha minus beta formula. And here's how we're going to do it. Let's write down the distance between those 2 points. What is the distance from this point to this point? And we're going to use the distance formula that we learned way back when. So let me write this in red. We've got the square root of, let's say, let this be x2 minus y2. Oh, sorry, x2 minus x1, y2 minus y1. You end up with cosine of alpha minus cosine of beta squared plus the difference of the y, sine of alpha minus sine of beta quantity squared. That would be the distance or the length of that line. All right, again, let's just make sure we understand what we're doing. This is, I'm going to call it that line L. This is the length of L. But this is also L over here, so it's going to be equal to, and now we've got a different 2 points, right? We've got cosine alpha minus beta, sine alpha minus beta, and 1, 0. So we take the difference of the x's, so cosine of alpha minus beta minus 1 squared plus sine of alpha minus beta minus 0. So you end up with just squared. I think I may have gone off the edge here. That's a squared. Okay, with that said, let's square both sides. So you have cosine of alpha minus cosine of beta quantity squared plus sine of alpha minus sine of beta quantity squared is equal to cosine of alpha minus beta minus 1 quantity squared plus sine of alpha minus beta quantity squared. All right, now let's do some algebra. Let's multiply out these terms. So multiply out the squares, which, remember, you'll have to use FOIL to do that. I'm going to skip the step of actually writing it all the way out. I'm just, writing out cosine alpha minus cosine beta times cosine alpha minus cosine beta. I think we can do this in one step by doing cosine squared of alpha minus 2 cosine alpha cosine beta plus cosine squared of beta. That's this first term. So this here expands to all of this. Okay? Now, do the next one. Plus sine squared alpha minus 2 sine alpha sine beta plus sine squared of alpha. So all of this became all of this. And then do the same thing on the right hand side. Equals. And I'll have cosine squared of alpha minus beta minus 2 cosine of alpha minus beta. I'm going to have to go down to the next line. Plus 1. And now all of this became all of this. Plus a sine squared of alpha minus beta. Now here's what I want you to see. Look at this plus this. Cosine squared plus sine squared of the same angle is always 1. Okay? But the same thing happens here. Cosine squared plus sine squared. By the way, that should have been a beta. You saw me write alpha and thought beta. That's a beta because it's this guy squared here. Alright, so beta squared, sine squared beta plus cosine squared beta is another 1. And so you're left with a minus 2 cosine alpha cosine beta minus 2 cosine alpha, nope, I said cosine, sine alpha, sine beta, that's this one, and this one. Okay, now on the right hand side, what do we have left? We have a cosine squared and a sine squared, which is going to give me a 1. We have this other plus 1 from here, minus 2 cosine of alpha minus beta. Now notice you've got a 1 plus 1, which gives me a 2, but you've also got a 1 plus 1 over here that gives me a 2, and if you subtract 2 from both sides, they're gone. And so what I have left is negative 2 cosine of alpha cosine of beta minus 2 sine of alpha sine of beta equals negative 2 cosine of alpha minus beta. And if you divide everything by negative 2, you end up with cosine alpha, cosine beta, plus sine alpha, sine beta equals cosine of alpha minus beta. And there is our first sum formula. Actually, it's a difference formula because you've got cosine of alpha minus beta. Now, where does the sum formula come from is actually very simple. We don't have to repeat this whole process. If I want to know what is cosine of alpha plus beta, just remember that cosine of alpha plus beta is the same thing as cosine of alpha minus a minus beta. And I can apply that formula that we just derived. Everywhere there's a beta, put a minus beta now. Cosine of alpha, cosine of negative beta, plus sine of alpha, sine of negative beta. Just plugging in this negative beta into right there. Now on this side over here of that identity. And remember your even-odd properties. Says that cosine of a negative beta is cosine of positive beta. The negative sign drops out. But with sine, this minus sign right here is going to come out front. So you have minus sine alpha sine beta. And so cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta, proved. Right? And that is why these formulas right here hold. Okay? So that's what we get. One of the things that the sum formula allows us to do is to find trig functions values for angles that aren't in our typical family of functions. For example, cosine of 75. 75 degrees is not in our 30, 60, 90 family or our 45 family. So what am I going to do? Well, I recognize the fact that I can rewrite this as cosine of 75 degrees is cosine of 30 degrees plus 45 degrees, both of which are in our special families of angles. And now using the sum formula says cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. So that's going to be, sorry about that, that's going to be cosine of 30, because that's my alpha, cosine of 45 minus sine of 30 sine of 45. Now the cosine of 30 degrees we know to be square root of 3 over 2. Cosine of 45 is square root of 2 over 2. Minus sine of 30 is 1/2. And sine of 45 is square root of 2 over 2. If we multiply those each out, we get square root of 6 over 4 minus square root of 2 over 4, or square root of 6 minus square root of 2 over 4. We have an exact value for cosine of 75. The next example asks us to find the exact value for cosine of pi over 12. And this one has the same problem as 75 degrees did above, in that it is not one of our special families. It's not pi over 3s or pi over 6s. It's pi over 12s. Now the trick here is to try to figure out two angles that either add together or subtract to give me pi over 12. Now the easiest way to probably do this is to think of pi over 12 as a degree. That is, convert pi over 12 to degrees by multiplying by 180 over pi. And the pi's cancel. 12 goes into 180 15 times. So this is 15 degrees. Can you find cosine of 15 degrees? Now thinking of it in terms of the angles that we do know, 0, 30, 45, 60, and 90, is there a way to add or subtract any of those angles together to get 15? And clearly we could do 45 minus 30, or we could do 60 minus 45. Either one will work. Let's do cosine of 45 minus 30 degrees. Okay, which will give me cosine of 45 cosine of 30 plus, and I'm using the formula for cosine of alpha minus beta now, which is the same as alpha plus beta, only the signs are swapped. So cosine 45, cosine 30 plus sine 45, sine 30. Square root of 2 over 2 is cosine of 45. Cosine of 30 is square root of 3 over 2 plus sine of 45 is square root of 2 over 2. Sine of 30 is 1/2. So you get square root of 6 minus square root of 2 all over 4 in this case. Now that we have a formula for difference of angles, we can actually apply it during our proofs or our establishing of trigonometric identities. In this case, the left-hand side of this identity is clearly the more complicated side, so we're going to start from there and try to turn it into the other side. Okay? Now what can we do? What identity can we apply? Well, clearly we can use cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. In this case, alpha is pi over 2 and beta is theta. So we have cosine of pi over 2 cosine of theta plus sine of pi over 2 sine of theta. Now cosine of pi over 2, cosine of 90 degrees, if you have to look it up, go right ahead, but that's the x-coordinate up here, so that's 0 times cosine of theta plus sine of pi over 2, which is a 1 times sine of theta. That's going to give me 0, and 1 times sine of theta is simply sine of theta, which is what I was trying to prove, so done. Now let's move on and look at the sine formulas for sum and difference. So it turns out, and we'll show this, that sine of alpha plus beta is the sine of alpha cosine of beta plus, and in this case the signs match instead of being opposite as they were for the cosine, sine or cosine alpha sine beta. So notice it's sine cosine, cosine sine. And for the sine of alpha minus beta, it's sine of alpha cosine beta minus cosine alpha sine beta. But of course, we want to answer the question of why is that the case? Why is that true? And it turns out that the easiest way to prove that is to use a little identity that we just proved, which was this guy right up here. This actually says that sine and cosine are related in that you can rewrite a sine of theta as cosine of pi over 2 minus theta. And the reason why that's helpful is then I could take, for example, if I wanted to find the formula for sine of alpha plus beta, think of this whole thing as my theta. Then I can rewrite that using cosine of pi over 2 minus theta is sine of theta. So I can rewrite this as cosine of pi over 2 minus alpha plus beta, or minus theta. And with just a little bit of manipulation, distribute this. I can rewrite this as cosine of pi over 2 minus alpha minus beta. And I'm going to group these together now. And now I'm going to apply the difference formula for cosine. This becomes cosine of pi over 2 minus alpha cosine of beta plus sine of pi over 2 minus alpha sine of beta. Now we know cosine of pi over 2 minus alpha is sine of alpha. So you have sine of alpha cosine of beta plus, turns out this is the same thing as cosine of alpha now. So you have cosine of alpha sine of beta. Now this proof can be done similarly. I left that out, but the fact that sine of pi over 2 minus alpha is cosine of alpha can be proven directly from that formula right there. Just replace theta with pi over 2 minus alpha, and this becomes alpha when it's all simplified. So this now is our proof of this formula right here. And as we did before, I can do sine of alpha minus beta by doing a sine of alpha plus a negative beta, which gives me sine of alpha cosine of negative beta plus cosine of alpha sine of negative beta. And this just becomes, the cosine up here becomes cosine of beta. And this cosine is the same. This minus sign comes out front, so instead of a plus here, you have minus sine of beta proved. Now we're asked to find the value of sine of 7 pi over 12. And again, I think it's probably easiest for most of us if we think of this in terms of degrees instead of radians. The problem with radians, of course, is the fraction form and being able to see that this is two like pi over 3s or pi over 4s added together. It's easier to think of it in terms of 30, 60, 90, and 45 degree angles. 7 pi over 12, if we convert to degrees, we'd multiply by 180 degrees over pi. The pi's cancel, and so I end up with 7 times 15 degrees, because 12 goes into 180 15 times. And that gives me 105 degrees. Now again, think of it in terms of 0, 30, 45, 60, 90 degrees, and all the multiples of those, we can find the exact value for those trig functions. Now, we can't find the exact value for 105 directly, but we can see that if I were to add 45 and 60, I get 105. So this is sine of 105 degrees, but that's sine of 60 plus 45 degrees, both of which we can find the exact trig function values for. Now, applying the formula we just wrote down above is going to be sine of 60 cosine of 45 plus cosine of 60 sine of 45. So sine of 60 is the square root of 3 over 2 times square root of 2 over 2 plus 1/2 times square root of 2 over 2, which gives me square root of 6 over 4 plus square root of 2 over 4 all over. So it's all over 4. You see that common showing up because of the nature of getting square roots of 3 over 2 and 1/2 showing up for sine of 60, cosine of 60. But that's the answer to that question. Now the next question actually allows us to apply the formula in reverse. So in this case, we see that we've got sine, cosine, cosine, sine. So we know it's a sine of a sum or difference. And because this is minus, and we know with sine functions the sign matches, that is with the sum and difference formula, these signs right here match. If I got a minus between a sine, cosine, and a cosine, sine, then this is going to be alpha minus beta. That's what that formula is the same thing as. So we're just going in reverse. But in this case, I can go ahead and find sine of 80 minus 20 is sine of 60 degrees, which we know to be the square root of 3 over 2. If it is known that sine of alpha is equal to 4/5, and alpha is between pi over 2 and pi, and that sine of beta is the negative 2 over the square root of 5, where beta is between pi and 3 pi over 2, we want to find the value of cosine of alpha, cosine of beta, cosine of alpha plus beta, and sine of alpha plus beta. Now, parts A and parts B are problems that we've already done previously in our homework. And let's go ahead and tackle it. If we do sine of alpha equals 45, we know that because the sign is positive, it's going to be in the upper half plane, but this right here tells us that it's in the second quadrant. Okay, so we got some point over here in the second quadrant. And since sine of alpha is equal to 4/5, and we know that from the theorem about the relationship of the definitions to non-unit circles, we can call the top value y, the bottom value r, and then solve for what the x-coordinate of that point would be. So if we're at a radius of 5 away, and we know that the y-coordinate is 4, we use x squared plus y squared equals r squared, which gives us x squared plus 16 equals 25, or x squared equals 9. So x has to be 3, and because we're in the second quadrant, x is going to be a -3. So that tells me, A, that cosine of alpha would be x over r, which is -3/5. Okay, now for the second angle, I know that it is in the fourth quadrant because beta is between pi and 3 pi over 2, and we've got a point out here, and we know that sine of beta is -2 over square root of 5, so we let y be -2 and r be 5. So again, using x squared plus y squared equals r squared, we end up with x squared plus a -2 squared equals square root of 5 squared, or x squared plus 4 equals 5. So x squared equals 1, which means that x has to be the square root of 1, which is 1, but because it's in the third quadrant, it's going to be a -1. So part B, cosine of beta is again x over r, so you get -1 over the square root of 5. And that's for the r down for beta. Now for part C, we can use our formulas to expand this sum formula for cosine. That's cosine alpha, cosine beta, minus sine alpha, sine beta, which would mean cosine of alpha, which we know to be -3/5 from here. Cosine of beta, which is -1 over square root of 5. Minus, now sine alpha is given to us as 4/5, and sine beta is -2 over square root of 5. Multiply that out, I get a +3 over 5 square roots of 5. Plus, because a minus times a minus is plus, 8 over 5 square roots of 5, which is 11 over 5 square roots of 5. And to rationalize the denominator, I will multiply by root 5 over root 5 and get 11 square roots of 5 over 5 times 5 is 25. Okay, part D, I'm running out of space and I apologize for that. Part D is going to be sine of alpha plus beta, which is sine alpha cosine beta plus cosine alpha sine beta, which is 4/5 times cosine beta, which is -1 over square root of 5, plus cosine alpha, which is -3/5 times sine of beta, which is -2 over square root of 5, which gives me -4 over 5 square roots of 5 plus 6 over 5 square roots of 5, which is a 2 over 5 square roots of 5, or if I multiply by root 5 over root 5, gives me 2 root 5 over 25. Done. In this example, we're establishing the following identity, and this one's actually pretty simple. It's just a matter of applying the difference formula for sine. So sine of pi over 2 minus theta would be sine of pi over 2 cosine of theta minus cosine of pi over 2 sine of theta. Sine of pi over 2, that's the y coordinate at 90 degrees, is a 1. So 1 times cosine theta minus cosine of pi over 2 is 0 times sine of theta, which gives me just cosine of theta. Done. The next proof asks us to show that the cosine of alpha minus beta over sine alpha sine beta is cotangent of alpha cotangent of beta plus 1. In many of our previous proofs, it was a good idea to convert everything to sines and cosines. In this case, the natural starting place is on the left-hand side because you've got a difference formula that you can apply immediately. So if I start with cosine of alpha minus beta on top over sine alpha sine beta, this is going to become cosine of alpha cosine of beta plus sine alpha sine beta divided by sine alpha sine beta. Now, using the distributive property, if you've got a sum divided by a single term, which single meaning it's all multiplied together, you can rewrite this as this fraction plus this fraction. Which would give me cosine of alpha cosine of beta divided by sine of alpha sine of beta plus sine alpha sine beta over sine alpha sine beta. Now, cosine of alpha over cosine of beta is my cotangent of alpha, and cosine beta over sine beta is cotangent of beta plus, and now these all divide out. You get the same thing on top and bottom, so you get 1, which is exactly what we were trying to prove. Now, I've gone ahead and included the sum formula and the difference formula for tangent here in your notes. Notice they are a little bit different looking in the fact that they are fractions, and the fractions show up again because of the relationship between tangent and sine and cosine. Tangent of alpha plus beta is going to be a sine of alpha plus beta over cosine of alpha plus beta, which is exactly where we can get this formula and show that it's true. Tangent of alpha plus beta would be sine of alpha plus beta divided by cosine of alpha plus beta, which we know sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta divided by, and this is going to be cosine of alpha cosine of beta plus sine alpha, actually minus sine beta. And we're trying to show this formula here. Now you got a little, I guess, creative algebra in order to turn this back into something that involves only tangents. If we leave it in the form that it is right now, we've got a sum formula for tangent in terms of sines and cosines. And while that may be helpful, we prefer to be able to convert it from tangent of the sum of angles to tangent of the individual angles. So to do that, I'm going to do the following trick. I'm going to take all of this numerator and all of this denominator and multiply it by the same thing on top and bottom. I'm going to multiply by 1 over cosine alpha cosine beta. And I'm going to do the same thing on bottom. I'm going to multiply by 1 over cosine alpha cosine beta. Now, it's not too hard to see where this comes from. If I multiply by 1 over cosine alpha cosine beta times this first term, I get sine alpha cosine beta divided by cosine alpha cosine beta. It's a good choice because these will cancel and leave me with a tangent of alpha, because sine over cosine is tangent. And that same choice will do the same thing for the second term. I end up with cosine alpha sine beta on top divided by cosine alpha from here, cosine beta. The cosine alphas cancel, and I'm left with a tangent of beta. And that's the entire numerator. If I do the same thing on the denominator, I'll have cosine alpha cosine beta over cosine alpha cosine beta minus sine alpha sine beta over cosine alpha cosine beta. There's another tangent, and these all cancel out and leave 1. So what I end up with is tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha tangent of beta, which is exactly what I wished to prove. Now I'm going to skip proving the second one, but realize it's exactly the same as what we did to prove the second one for both the cosine and the sine, which was to replace a beta with a negative beta throughout the formula, in effect changing this sign here and this sign here, because the minus sign comes out from minus beta here and here. That's why it changes those signs inside there. This example shows that the tangent of an angle plus pi, in other words, adding 1/2 of a rotation or scooting the tangent function over a distance of pi, when you look at its graph, ends up being the same thing as just tangent. But we can prove that now using our sum formula for tangent. Remember, tangent of theta plus pi would be tangent of theta plus tangent of pi divided by 1 minus tangent of theta tangent of pi. But tangent of pi is 0, which means on top I just have tangent of theta, and on bottom I have 1 minus 0 times tangent of theta, which is 0, or just 1 on bottom, which gives me tangent of theta proved. On this one, we're asked to establish the identity tangent of theta plus pi over 2 is negative cotangent of theta. Alright, so let's try tangent of theta plus pi over 2. Problem. And what is the problem? If I do tangent of theta plus tangent of pi over 2 over 1 minus tangent of theta tangent of pi over 2, these two values are undefined. So we cannot actually do that problem using the sum of angles formula directly. However, we're not out of the realm of possibility. Let's go back and just think of tangent in terms of what we know it to be in terms of sine and cosine. What if I did sine of theta plus pi over 2 on top and cosine of theta plus pi over 2 on bottom? Well, that's going to give me a sine of theta cosine of pi over 2 plus cosine of pi over 2 sine of theta. On bottom, I'll have cosine of theta cosine of pi over 2 minus sine of theta sine of pi over 2. Now all these pi over 2's I can do. Cosine of pi over 2 is 0, and I got this wrong. I need to fix this. Sorry. Let's go back and fix what I just wrote. This should be cosine of theta sine of pi over 2. That's a 1. And then cosine of pi over 2 is 0. Sine of pi over 2 is 1. So these whole terms, the first terms on bottom and top, end up being 0. So I have cosine of theta times 1 over negative sine of theta times 1, which gives me a negative cotangent of theta proved. In this last example, we're asked to find the sine of the cosine inverse of 1/2 plus the sine inverse of 3/2. Now, it's a combination of different types of problems. You've got inverse functions here, And the thing to remember with inverse functions is that their output is an angle. Right? Cosine inverse of 1/2 is the angle from 0 to pi, whose cosine is 1/2. Right? And since it's positive, you know it's going to be over here. If I call that angle alpha, we've got some alpha over here. Now, for the other one, that is the angle from negative pi over 2 to positive pi over 2, whose sine is 3/2. Since it's positive, we also know that that angle, let's call it beta, is in the first quadrant. So really what you have is a sine of alpha plus beta. And what we know about alpha is that cosine of alpha is 1/2. And we know that sine of beta is 3/5. And we know that because we're told that alpha, or we assigned alpha to be cosine inverse of 1/2 and beta to be sine inverse of 3/5. But in order to do this, we'll need to know not only cosine of alpha, but sine of alpha. And we'll need to know cosine of beta as well, even though we already know sine of beta. So how do we figure that out? Well, we go back and use the fact that if cosine of alpha is 1/2, we'd let the 1 be our x and the 2 be our r, which means that x squared plus r squared equals, or plus y squared equals r squared. That's 1 squared plus y squared equals 2 squared. So y squared is 4 minus 1, or 3. So y is the square root of 3. And it's positive because I'm in the first quadrant. For sine of beta equals 3/5, that means I would let y be 3 and 5 be r. So x squared plus y squared equals r squared means that I have x squared plus 3 squared equals 5 squared, or x squared plus 9 equals 25. So x squared is 16. So x has to be a positive 4. And what this means is for cosine of alpha, I can also find sine of alpha, which would be square root of 3 over r, which is 2. And for sine of beta, I know 3/5 is the sine of beta. Cosine of beta would then be x over r, which is 4 over 5. So plug all of these values in to this guy. And you're left with this equals sine of alpha, square root of 3 over 2 times cosine beta, which is 4/5, plus cosine of alpha, which is 1/2, times sine of beta, which is 3/5, which gives 4 square roots of 3 plus 3 all over 10. And we're done.